It was 1985 when I went to Control Data Institute in the Los Angeles area, and one of my instructors was Mr. Marion Polite. And this gentleman was the most effective teacher I had in my early years in IT. And I am eternally grateful. So if there's anybody listening to this nugget who is a relative or a descendant of Mr. Marion Polite, I want to thank you for his amazing impact on me. Because when I was in school, he did not let us get away with anything. We were working with processors like the 8086 and wiring them up, and working with registers and pointers. And although I didn't take the path of programming as my primary emphasis, he did instill in me the interest and an understanding of how microprocessors and instruction pointers and memory access and registers all worked. And I was reminded of that when I was going to create this nugget on buffer overflows. So I wanted to share that happy thought with you that I was having as we jump in together and take a look at not only what buffer violations are and how memory address space can be compromised, but also take a look at what we can do to help mitigate or protect against that happening. The term buffer overflow usually refers to several different classes of exploits or issues with applications and how they are using or misusing memory. And that's effectively what a buffer overflow or a buffer overrun is. It's a violation of memory security. For example, let's say we have an application that is running on a computer. Now, as we all know, applications need memory to run, to execute. So if this is a graphical representation of some memory, in fact, we could go ahead and refer to this as a heap of memory. Very similar to clothing. For example, if we take our clothes out of the dryer and just dump them on the ground, we've got a heap of clothing. Well, we could refer to a pool of memory as a heap of memory. And a heap includes sections of memory where that application can store its information. There's also an organization of memory called a stack. That's also referring to memory. So when people refer to buffer overflows, they could be referring to a heap-based or a stack-based buffer overflow or misuse of memory. And one of the questions that may come up is, okay, how exactly does an application get a dynamic allocation of memory, get its allocation regarding the heap? And in C programming, there's a function called malloc, which can be used to go ahead and allocate memory dynamically on the heap for an application and its processes to use. So when an application has been dynamically allocated memory, and let's go ahead and label these. Let's label it area 1, 2, 3, and 4. And these could be memory areas related to the heap or the stack. The application is going to use these memory areas for storing information. And then as the application executes code, there may be instructions to go ahead and go to this area and execute the code there, and then go to this area, and then at the end of that, go back to area 1, look for some other variable, and then continue processing. And one of the mechanisms we're going to use in an application is called a pointer. Let me go ahead and change the color so it's a little more readable. Pointer. And the pointer concept is applicable for memory in the heap as well as memory in the stack. So what if an attacker could compromise a vulnerable application by injecting content? And let's say we inject content right here. We'll call this attacker content. So now the attacker's malicious content has been injected into memory. And then when the application is running, if we can trick the pointer into pointing over to this section, for example, it processes section 1, then section 2, and then the return address, the pointer for the next executable code, points over now to area 3. The attacker is now going to have his code executed or run because he's messed up the pointers. And now we have a compromised system. And the term stack smashing is a buffer-related attack where we have overwritten or corrupted or changed the return address, which is what allows an attack like this to happen. So a stack buffer overflow could be referred to as stack smashing. And if the attacker has the ability to modify or manipulate that pointer, besides pointing to his own corrupted buffer area that has his code there, he could also jump to a function in the application or one of the app's libraries, which could cause the program to stop working. And just by doing that, we could have a denial of service if the application crashes or stops functioning. Now, one of the challenges of working with memory, especially if you're trying to hack it, is that there are millions of locations that could be referred to as addressable memory space. So to have a pointer go to the exact correct space in memory might be a little bit challenging. So one technique that the attacker can use is called the no-op, which is an acronym for no operation. It's basically a cycle of about a nanosecond, a splinter of a thought in a computer's brain. And the attacker could go ahead and create a fairly wide swath of no operation statements. And think of it like this. If you and I are flying an airplane and we're going to land that sucker, do we want a nice, long, big runway? Or are we looking for a small, barely long enough runway? And for me, because I'm not a pilot, if I'm doing this for the first time based on my experience with Flight Simulator, I'm looking for a big old runway with plenty of leeway. So by planting a whole bunch of no-ops, so let's say the no-ops are all this red stuff here, and then we have the code at the bottom, the attacker only really has to get anywhere in this space. And if he ends up in the middle, the no-ops will simply be processed all the way down until they get to the code, and then his code can be executed. So we can think of a set of the attacker's no-ops as a bigger landing strip or runway, so that the attacker just has to hit anywhere in there to allow his code to eventually run. And that's also referred to as a no-op sled. SLED, because we're effectively sliding all the way down to the code. So we could think of all of these no-ops as padding, creating a no-op sled to make it easier for the attacker to find or correctly point to the area that leads to his code. And that padding in memory is just to help ensure that the buffer overflow will be more likely to succeed because the pointer doesn't have to be exactly spot on. We have some wiggle room. And the reason the attacker would do something like this might be a denial of service attack. They just want to take down the system. Or they want to run malicious code that's going to give them access to the box, and in doing so, bypass security or temporarily run an executable at root or admin privilege levels that could open ports on the system and run services so the attacker could in the future connect to that system and own it. Or perhaps the malicious code is going to create a reverse shell, which causes the victimized machine to create a connection out to the attacker. And the reason that can work is because we're executing the code to do that at elevated privilege levels. And as that code continues to run, it continues to have that same level of privilege. Now, regarding the apps that computers run, there can be compiled applications that are ready to be processed by the machine. There's also programming languages that use an interpreter that dynamically interpret the commands before they're processed by the CPU. Now, two programming languages that are very popular, but they're also susceptible to buffer overflow attacks are C and C++. Because they don't by default have built-in boundary checks regarding memory. So for example, if an application has been written that uses the function strcpy and then some data regarding the input of a string, if there's no checks regarding what string is going to be input, that opens the door, the vulnerability for an attacker to inject the malicious code while that app's being used. So just like in SQL injection and other web-based applications, to help avoid buffer overflows and the exploitation of memory areas, we'd want to make sure we do a lot of checking of data inside of our applications before that data is actually processed or put in memory by the application. So the secret here is input validation as one of our methods for protecting against overflow attacks. So without the checks and balances in place, when data is being written here, if it's more than this buffer can support, it might overflow into this buffer, and now the attacker's malicious code is sitting in this area waiting for a pointer manipulation to go ahead and point to this code to run it. So here's a Wikipedia article regarding code red from many years ago, back in 2001. It was huge then, and there have been many since then. And if we scroll down a little bit, it points out it took advantage of a buffer overflow, and it did this by using a long string of the repeated letter N to overflow a buffer, which allowed the worm to execute arbitrary code and infect the machine with the worm. And if we scroll down, it has an example of the code used as part of code red. So how could this have been solved? If the server was doing input validation, it should have seen, whoa, that's way too many characters for what we're expecting, which overflowed the buffer and allowed this code to be executed. Now, what can be done to protect against buffer-related attacks? And it's not just buffer overflows. It could also be issues of buffers being underread, or underwritten, or referring to not having accurate and complete control over the memory space, whether it's heap or stack, by the application or operating system that's using that memory. So here are some things we could do. We could have IDS/IPS, intrusion detection or prevention systems, that's looking before it hits the server. So we could have network-based or host-based intrusion detection or prevention, analyzing or looking for that type of data to prevent it from being executed by the application. However, one of the best ways of protecting against a buffer overflow type of an attack is great, and I'll put next to that secure code. Regarding doing boundary checking, every time we're either reading or writing from the stack or from the heap, to verify in the code that it's following the proper rules. And a big part of that is doing boundary validation regarding reads and writes from memory. And even if a programming language doesn't have those features on by default, most programming languages do have some of those features that can be enabled and used by the programmers. Another method that could be used is a cookie type mechanism. So let's say, for example, at this memory location, we put some value. Let's put A, B, C, 1, 2, 3 as a cookie. And then as the program is operating, before it goes back to that stack or that area of memory, it can check that location for that cookie. And guess what? If that value is not there, if it's different, that implies that something has been modified in memory. So the application could say, whoa, hold on, something is wrong, as opposed to continuing on with potential malicious code somewhere in its buffers. And that cookie is often referred to as a canary value. And just like a canary in a coal mine, they used to put them down there, and when the bird stopped chirping, that was a big red flag saying, whoa, something is wrong. Well, if we go back and look at the cookie, or this canary value, and it's changed, that's the red flag that something is wrong, that there might be some overwriting or manipulation of buffers outside of the application, its processes, and its normal functions. And they can be used to monitor and look for buffer overflows. And to implement canaries, there was a set of patches introduced back before the year 2000 called Stack Guard that could be used to help identify stack smashing and prevent it. An additional option that we could use is regarding our pointers. We could copy a return address, put it somewhere else in memory, and then before we use that return address, go verify that return address to make sure that the return address that we have copied to a separate location matches the return address that we're about to use. That's also a lot like comparing two hash values to make sure that there hasn't been tampering or modification. We could also use applications to go through our code looking for weaknesses or vulnerabilities. One of those tools is called Splint, S-P-L-I-N-T. And it can go through and statically check for things, including code that may be vulnerable to buffer overflows. And that would also be a good way to help prevent a buffer overflow from being successful by helping to confirm that we have well-written code. We'd also want to have appropriate error and exception handling and logging. That way, if something does happen, we can look at what happened in the logs, and then from the log information, resolve the issues that came up if they're related to the code or the hardware that the code is running on. So all of these right here are software related, code related, but there's also options that we can do regarding hardware. Depending on the type of process that we're running, we might have the option of setting NX, which is for no execution, or XD for execution disabled, regarding certain pages or areas of memory. And that way when the processor, if it sees an area of memory that's being called, it can say, whoa, stop the truck. That's an area marked NX, non-executable, or execution disabled. And as a result, we can have hardware prevention from having malicious and unwanted code being run. And if we were doing penetration testing, with authorization of course, and we run an attack that does a buffer overflow and it's successful, and as a result, we're able to see all the data on that system, including sensitive information, maybe usernames and passwords that are stored, or private keys that should not be exposed, which by the way is a vulnerability from Heartbleed, which although it's not a buffer overrun attack, a system that is vulnerable to Heartbleed and compromised can reveal the private keys. In any event, if you and I are doing the pen testing and we do come across really sensitive information on a vulnerable system, we need to pause and report that to the proper people immediately so they can fix it. I'm glad you joined me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.